Welcome back everybody. Up until now, all the videos in this series about hashing have been quite theoretical. I've talked about general principles and ideas, but haven't really given much in the way of application of hashes and hash functions. So let's look at a little example of where the rubber hits the road. Let's imagine a scenario where we need to manage admission to a concert, and we want to use software to do it. The main thing we need to keep track of is who has been admitted to the concert, so that people can't duplicate tickets to allow multiple people in on a single ticket. By the way, if you haven't seen the previous videos in this series, I do refer to them and build on the explanations and principles in them, so I suggest you watch them first. I'll link them below. So let's give a bit of a definition of our sample problem. We have a capacity in the concert for 100,000 attendees and it's sold out. So we now need to keep track of 100,000 unique ticket numbers when people arrive at the concert. One of the simplest ways to do this would be to just keep a list of ticket numbers and check the list every time a new attendee arrives to see whether they're already on the list. And this is relatively quick and easy for a small number of attendees, but the process gets slower with every new arrival, as we have to check the number against every other number that's already on the list. Those of you who are algorithm geeks would know that this checking is an order n operation. This means that the time taken to perform the check increases proportionally to the number of items on the list. To give some real numbers here, let's say it takes 10 microseconds to check whether two ticket numbers are the same. This means that the checking process for the first attendee takes 10 microseconds, the second 20, the third 30, and so on. So this means that with the last few attendees, it takes nearly 10 seconds just to check whether they have a valid ticket. And this means that the total time spent checking will be nearly 14 hours. So we can see this isn't really practical, is it? So let's give some thought to how we can speed this up. One way we could do this might be to perform the checks in parallel, but that's not a really good solution for a few reasons I'm not going to discuss right now. Or another way we could do it is use the ticket number as an index into a list of ticket numbers. This would be really fast, a constant time process, or again for you algorithm people, an all-in-one operation. But it's only really efficient if the ticket numbers are all relatively close to each other. But what happens if the tickets happen to be randomly spread over a large range of, say, 1 billion numbers, is that in order to use this method, we would need to have a list that is 1 billion items long, and that could take a lot of space. In this case, 4 orders of magnitude more space than a list of just the numbers that we're using. So we can come to a better solution to the problem by thinking more about what we are actually trying to do. With every new attendee, we want to check the set of ticket numbers from every attendee who's already arrived, to see if the new attendee's ticket number is in that set. The keyword here is set, and I'm talking about the mathematical term set here. So what we need is some way to efficiently represent a set without the process of checking whether something's in the set is getting too long as more things are put in the set. In order to design a way of doing this, let's go back to the method we were considering of just using the ticket number as an index into the list. It's really fast, one of the fastest things you can do on a computer, but if the size of the list required is too big, then it's just impossible to do due to physical limitations of computer hardware. So something that's fast but can't be done, that's not really useful. What we need to do is find some way of storing the list in a smaller space without losing too much of the speed benefit of using the list like this. Basically, this means that we need to somehow map the ticket numbers into a more compressed range of values. If this is starting to sound familiar from an earlier video, you'd be right. In an earlier video, I showed that we could use the modulus operator to derive a constant length number from any other number. This is where another feature of hash functions that I've not mentioned yet is useful. A lot of hash functions run at a very predictable speed. In fact, in this case, given that our inputs, which are our ticket numbers, are of a constant length, or very close to, then we can say that if we choose the right hash function, it will always run the same amount of time no matter what ticket number we use as an input. So let's talk about how this will actually work. We know we have 100,000 attendees, So we know we need a list at least 100,000 items long. For reasons I'll explain in a minute, let's say we use a list of length 300,000. Now for a hash function, let's use the nmod_m function I mentioned in a previous video. And I'll define it in this case more specifically as nmod 300,000. This will ensure that the indexes we generate with this hash function are valid indexes for our list. And at this point, by combining the list and this hash function, we have a basic hash map. We can take any ticket number as an input and generate an index into our list from it. And then we can indicate at that index in the list whether that ticket has been used to enter the concert, and we don't have to check every other item in the list to check a ticket, just that one item. Now unfortunately in practice it's not quite this easy, and nothing much ever is in the software world. The biggest complication is the reason that we wanted a list that was longer than the number of tickets that we want to handle. And the root cause is a limitation of hash functions that I mentioned early on, and that is collisions. This is where two inputs to a hash function produce the same output. This could lead to two tickets with different ticket numbers ending up indexing the same item on the list. There are many mitigations and solutions that have been devised to deal with this, but just to show a way it can be done, here's the simplest solution to this problem, called linear probing. To do linear probing, we need to do two things. Firstly, we're going to store the ticket number in the list at the index. This allows us to check that the ticket number at the index matches the ticket number we use to generate the index. If the item at the index is empty, obviously we can just add the ticket number as a new item and move on, because we know we have a new ticket number that hasn't been used to enter it before. If it matches the item at that index, we know that the ticket has already been used and we can stop the person from entering the concert. If the item in the list is not empty and it does not match our ticket number we're checking, is where linear probing comes in. What we then do in linear probing is increment the index to the next item in the list. Once again, we follow the same process. If it's empty, we add the item. If it matches, then we know it's already in there and we reject it. But if it's not empty and does not match, we repeat the process again and increment the index. And we just keep doing this until we either get a match or we find an empty list item. The addition of the extra list entries over and above what's needed to hold all the ticket numbers, that is 300,000 instead of 100,000, is to reduce situations where this incrementing has to be done many times in a row, which would make it slow. So on the whole, this somewhat larger list gets us very close to a constant time check on the ticket number without requiring a very large list. If we assume that an individual check now takes longer than the original check, which was 10 microseconds, and it's now 1 millisecond, which is 100 times longer than our original. This means that all the checks will now take about 100 seconds all up, which when compared to the original time of nearly 14 hours, I think makes the point that this is a good trade-off where the individual checks are longer, but the overall time is much, much shorter. So that just about sums up how we can design a simple hash set that uses hash functions to allow us to check things relatively efficiently. Thanks for listening, and I hope it helps.